Now, for this problem, what we have is that we are told there are some objects that are the spheres of radius r that are falling through a stream of air that moves at a certain speed. And we're told that the resistive force has this shape, so it has a term that depends on the radius times the velocity in a linear way, and we have a quadratic term that goes like, oh, the radius squared times the velocity squared. We're given some values for a and b, assuming they're appropriate MKS units. I want to find, okay, what is the terminal velocity of the sphere? So when the sphere is at its terminal velocities and the net forces acting on it have to sum to zero. So the only other force, since this is falling, the only other force acting on it is the gravitational force, which is the weight. So we write out this equation is equal to 0, and this implies that we have a second order polynomial for the terminal velocity that looks like this. Now, for the rest of the problem, we will assume that these spheres are just water droplets, and we know that the density of the water is given by this quantity, 997 kilograms per meter cubed. So we're going to write the mass and use this density times the volume, and this is the volume because we know it's a sphere. And we plug that in into our second degree polynomial for the terminal velocity, or less with something that looks like this. Now, what we're going to do is we're going to plug in the numerical values for A, V, rho, G, and G, or we still don't know R. And plugging into the appropriate numerical values, we have this right here. Now, to find the terminal velocity, all we have to do is solve this quadratic equation, and we all know how to solve quadratic equations at this point. And we'll only take the positive solution, so we'll only take the positive root of this polynomial because we're only interested in physical solutions. And using the quadratic equation, we find that the terminal velocity is going to look like this as a function of the radius of the spherical object. We have 1 over r here, we have a 1 over r squared, and we have a term proportional to r inside the square root. So now what we're going to do to finish off the problem is I want to consider 3 different values of the radius. First, we're going to consider 10 to the minus 5 meters, and that gives us this terminal velocity, 0.0132 meters. And 10 to the minus 4 meters gives us 1.03 meters per second terminal velocity. And finally, 10 to the minus 3 meters gives us 6.87 meters per second. And now notice how the terminal velocity increases with the radius. And we can sort of see that here, in case that as the radius increases, which of these different terms here becomes more important, which one becomes bigger.